In section 3.4, we're going to look at some counting principles. We've already seen one example of this earlier in the class, back in section 3.1, when we discussed the fundamental counting principle. Recall that the fundamental counting principle says that if you're going to complete a sequence of steps, and if the first step can happen m ways, and the second step can happen n ways, then the total of ways in which the total sequence can occur is going to be m times n. And furthermore, we saw that this event can be extended to any number of events, or any number of a sequence of events. For instance, let's suppose we have a student that must choose from 7 classes to take at 8 a.m., 4 classes to take at 9 a.m., and then 3 classes to take at 10 a.m. How many schedules can the student make? Well, typically, again, a good idea for this is to try to diagram it out. We have 3 selections to make. They have 7 choices for the first class, 4 choices for the second class, and 3 choices for the last class. Therefore, according to the fundamental counting principle, we just multiply 7 times 4 times 3, which would give us a total of 84 possible schedules. So that's one example of a counting technique we've already incurred. The next 2 we're going to deal with in this section are going to be what's called permutations and combinations. We'll start with permutations. And what a permutation is it's an ordered arrangement of items in which no item is used more than once. So this is going to be a selection without replacement. Let's suppose that we have from a collection of n items, we're going to be choosing r of them. And the thing that makes this very important is that under a permutation, order matters. For instance, if I have 2 letters, let's just simply say A and B. Under the guise of a permutation, A and B versus B and A would be considered different items because the order is different. Okay? There's a formula for this. The formula for the number of permutations is n factorial divided by n minus r factorial. So if you have n from a collection of n objects, we're choosing r of them where order matters. That makes it a permutation. And to do this computation, it's n factorial divided by n minus r factorial. The factorial button itself, in the calculator under the math menu, go over to the PRB option, and then you'll see it looks like an exclamation point. But for example, what factorial means, let me look at 3 factorial for instance, is you simply start with the integer the positive integer that you have, and you multiply all of the numbers starting from that number down until you get to 1. So 3 factorial would be 3 times 2 times 1, which is 6. If we wanted to do, let's say, 5 factorial, 5 factorial would represent 5 times 4 times 3 times 2 times 1, and that would give us 120. So the formula that involves permutations has this factorial notation attached to it. Okay. Let's take a look at example 2. This is one that we did previously where we figured it out. Suppose we're going to create a 4-digit access code and that none of the digits can be repeated. When it comes to things like an access code, obviously the order will matter. The code 1234 would be different from the code 4321. Even though it has the same numbers within it, the order matters, and that's what's going to make this a permutation. However, we've already done it with the fundamental counting principle, which would say that, well, if we can't have repeats, or if selection is done without replacement, then we had 10 choices for the first digit, 9 choices for the second, 8 choices for the third, and 7 choices for the last one, which would give us 5,040. We can also view this problem in the context of permutations. If we're choosing from the digits, we know that there's 10 digits altogether. We're picking 4 of them without replacement, and the order matters, so that's going to make this a permutation. To do a permutation in the calculator, what you would first do is put the n number. This is how many items you have to choose from. You would then go to the math menu, go over to the probability menu, select option 2, which is NPR, and then simply put in how many of those items are you selecting. And because order matters, that's what makes it an NPR. We hit enter, and we see yet a separate way where we can get the 5,040. Let's take a look at example 3. In example 3, it says, suppose you are a coach at a Little League baseball team. If there are 13 players on the team to choose from, we're going to select 9 of them to create a batting order. Okay? And as kind of the name implies here, the order matters. Where you put someone to bat makes a huge difference whether they bat leadoff, which would be first, or whether perhaps they bat cleanup, which would be fourth position. So here we have 13 people to choose from. We're selecting 9 of them, and because the order matters, again, this will be a permutation. So it's going to be 13p9. Let's punch that into the calculator. So we have 13. Go to math. Over to the probability menu. NPR 9. Hit enter. And we would get that there's a total of 259,459,200 different possible batting orders that would be created. Take a look at another one. Let's suppose that we have a Boy Scout Derby that's a race that has 12 entries. Assuming there are no ties, in how many different ways could the individuals finish first, second, and third? So we have 12 individuals to choose from. We want to know how many different orders can the top 3 occur. So we're selecting 3 of them, and because order matters, it's still going to be a permutation. So this would be 12p3, 12, we go over to math, NPR, then hit the R button, which is how many we're choosing from. So from a collection of 12 items, we're selecting 3 of them where order matters, so that's 12p3, which would give us 1,320 different ways. Again, this is one that you could have even done with the fundamental counting principle. If we think about the top 3 finishers, there's 12 ways for the first person to finish. Let's say if that's for the first person. Then there'd be 11 people that could finish second, and then we'd be down to 10 people to finish third, and that would also give us the 1,320. The next thing we're going to look at is a combination, and in a combination, the order does not matter. So we're still going to be doing selection without replacement, but order does not matter. So under the scheme of a combination, let's suppose you pick 2 letters, A and B, or B and A would be counted as exactly the same element, because they both contain the same 2 letters, and under a combination, order does not matter. We give this the notation NCR. So from a collection of n objects, we're selecting R of them where order doesn't matter. That makes it a combination. The formula for a combination, n choose R, this would be equal to n factorial divided by n minus R factorial times R factorial. Let's take a look at an example of some combinations. Let's suppose that Baskin-Robbins offers 31 flavors of ice cream. One of their items is a bowl with 3 scoops of ice cream, and we're not going to do any flavor repeats on this one. How many different bowls are possible? So we have 31 flavors to choose from, and we're going to pick 3 of them. Okay. As an example, let's just suppose you go with the tried and true classics, strawberry, vanilla, and chocolate. It doesn't matter in what order those 3 ice creams get put into your bowl. Once you receive that bowl, it's still going to have the same 3 flavors. So what that's telling us is that order does not matter in this case, and that's what's going to make it a combination. So this would be 31, math, go over into the same menu, probability, choice 3, and now we're selecting 3 of them. So from a collection of 31 objects, we're choosing 3 of them, where order does not matter. That makes it a combination, and we get 4,495. Let's take a look at example 6. They say calculate the probability of winning the SC Powerball lottery. To play the Powerball lottery in SC, what we need to do is match 5 numbers. They're going to come from 1 through 55 in any order. And then also we have to match the Powerball, which is just one number from 1 to 42. Assume the numbers are not repeated, so no number can be drawn more than once, and the order does not matter. So as long as you match precisely the numbers that are drawn, no matter what order they show up on your ticket, that would mean that you would be a winner. And notice here, we're not just simply asking about the count. We want to go one step further and compute the probability. Okay. Let's think of the creation of this ticket as being a two-step event. So the first step would be the matter of selecting the first 5 numbers. And we know that for the first 5 numbers, we have 55 to choose from. We're going to select 5 of them, and order does not matter. So that would be 55, math, PRB, NCR 5. So choose 5. I'm not going to enter that into the calculator, but you can see the value here. If you do plug it in, that would give you 3,478,761 different ways. So that's the number of ways in which we can select the first 5 numbers without order mattering. Once we choose the first 5 numbers, we now need to go ahead and choose the Powerball. There's 42 numbers to choose from. We're selecting one of them, so where the order does not matter. So that's going to be 42 choose 1. And now, as a subpart of this, we're using the fundamental counting principle, which says this is the number of ways we can do the first step. This is the number of ways we can do the second step. And once you pick the first 5, once you pick your Powerball, that will give you your ticket. And I'm just going to do it as one big old multiplication in the calculator. But what you would see is that there's going to be 146,107,962 different possible lottery tickets available. So that's the total number of different tickets where order does not matter. And if we want to calculate the probability that we win, well, there's going to be just simply one winning combination out of those 146 odd million possibilities, which would give us a probability of 0.0000000684. Not only is it an unusual event, it would be an extremely rare and unlikely event. So, if anything, if you want to play the Powerball for entertainment value, or if you find it fun, then that's one thing. But based upon the probability of winning, don't expect to win on a given trial because the probability is so low. Let's take a look at another one. In example 7, we're told that a restaurant offers a dinner special where we have 12 choices for entrees, 10 choices for side dishes, and 6 choices for dessert. If we can choose 1 entree, 2 side dishes, and 1 dessert, how many different meals are possible? Okay. This problem actually is a little bit vague. We'll work through it in terms of kind of the expected solution, and I'll give you another answer to this one as well. So if we want to think about how many different meals are possible, again, break it down. We're going to do a combination of counting methods here. First thing we're going to approach is, let's think of it like a multi-step procedure. So we're going to use the fundamental counting principle. In order to create a meal, we first need to choose an entree. Then we're going to choose our side dishes. And then we're going to choose our dessert. Well, we have we need to choose 1 entree from a collection of 12. And once you have these things on your plate, the order in which they're put does not matter. So these are going to be combinations. So there's 12, choose 1 for the number of entrees. Now for the sides, we have 10 sides to choose from. And we're going to pick 2 of them. It doesn't say that we can't repeat sides. It's kind of implied because it's in this section. But if you don't allow for repetitions, then this would be 10 choose 2. And then to choose a dessert, it would be 6 choose 1. So if we multiply it out, 12 choose 1, that's 12. 10 choose 2 is 45. and 6 choose 1 would be 6. So if we multiply them all together, that would give us a total of 3,240 different meals that are possible. Now, the one thing that they don't say is it doesn't say we have to choose 2 different side dishes. Okay? I'm personally a huge mac and cheese fan. If I can do double mac, I typically will go for that. So the way that would change this problem would be the following. So we could do our one entree. That's going to be 12 choose 1. Now, the second step changes because if you do allow for repetitions, then it no longer becomes either a combination or a permutation, because both of those are done under a selection without replacement scheme. The second step will look like this. If you have 10 choices for the first side dish, and if they allow repetitions, then you could choose any one of those 10 side dishes again for your second pick. And then lastly, we have 6 choices for dessert, and we're only selecting 1, because we get 1 dessert, so that's going to be 6 choose 1. So if you allow for repetitions, you actually would get more possibilities. But we're going to assume that when they say 2 side dishes, we'll assume that they mean 2 unique side dishes, in which case we would get this as our answer. Let's take a look at example 8. A student advisory board consists of 20 members. 2 members serve as the board's chair and secretary. Each member is equally likely to serve in either of the 2 positions. What is the probability of randomly selecting the 2 members who currently hold the 2 positions? So this one here, we're choosing 2 people. And what's going to make this one a little bit different than the last couple is that there's names to the positions. So they give some weight or essentially some ranking or ordering to those spots. Somebody being chosen to serve as chair would be a different committee than if that same person was chosen as a secretary. So, in essence, the order in which they're picked will make a big difference here. And that's going to turn it into a permutation. From a collection of 20 individuals, we're selecting 2 of them where the order matters. So this is going to be a permutation. 20 NPR2 would be 380. So there's going to be 380 different ways those 2 positions can be filled from the 20 board members. The probability that we select at random the 2 people that are in those given spots, well, that's just 1 committee out of the 380. So that would happen with probability 0.003. Let's take a look at example 9. Suppose marbles are drawn without replacement from a bag containing 10 marbles. How many samples of 3 marbles can be drawn? So we have 10 marbles to choose from, and we're going to choose a sample of size 3. If you were to actually execute this experiment, and you actually pick 3 marbles out of the bag, the sample you get is really kind of indifferent to when those marbles are selected. If you select the first red, the second red, and the third red marble all in one selection, those are the 3 marbles you have. So the order isn't going to be important here, which will turn this back into a combination. So from a collection of 10 items, we're choosing 3 where order doesn't matter. So this is going to be 10, choose 3. And that's 120. If we know further that the bag consists of 3 red, 2 green, and 5 black, how many samples of size 2 can be drawn that contain both black marbles? So how many different ways can we choose 2 black marbles out of this bag? Well, we have 5 marbles that are black to choose from, and we know that we're going to be picking 2 of them. The order will not matter, so it's still going to be a combination. This would be 5 combination 2, and that would work out to be 10 different samples. So there's 10 different samples consisting solely of black marbles that could be drawn from that bag. We'll finish with example 44. Suppose that in a certain state, each automobile license plate consists of 2 letters followed by a 4-digit number. How many license plates can be formed if there are, first of all, no restrictions? So, again, think of the creation of a license plate as being a series of steps. We have to choose 2 letters and then 4 digits. If no restrictions are in play, then we have all 26 choices for the first letter, all 26 for the second letter. We now come to the digits. We have 10 choices for the first, second, third, etc. Fundamental accounting principle says multiply those all together, and we would get 6,760,000 different license plate possibilities. In part B, we're going to alter this. They say, what if the letters O and I can't be used? Well, that's going to affect our first 2 possibilities. If we remove 2 letters from the alphabet, then we'd have 24 choices for the first letter, times 24 choices for the second letter. Notice that that's the only condition they give. They don't put any restrictions or stipulations on the digits, so we assume we'd have all 10 digits for each of our 4 numbers. So if we multiply those all together, we would get 5,760,000 different possibilities. And I always kind of find it interesting that if you just compare Part A to Part B, by simply removing 2 letters from the possibilities for the first 2 letters, we've actually lost 1 million different possible license plates that could have been created. Let's take a look at Part C. Part C says, what is the probability of selecting a random license plate that ends in an even number? Okay, so what's the probability of selecting a license plate that ends in an even number? So in order to compute this, remember what we're going to do is we're going to use the fundamental definition of probability. It's the number of ways an event can occur divided by the total number of possibilities. Here they don't say about any restrictions, so we already calculated the total number of different license plates that could be created back in Part A. That's the 6,760,000. That's going to go in our denominator. Now, how many license plates are going to end in an even number? Well, that's the only stipulation that's on here is on the last digit. So the first letter could be any one of the 26. Second letter could be any one of the 26. The first 3 digits can be any 10, 10, and 10. But because the last digit must be even, that means it has to be either the 0, 2, 4, 6, or 8, of which there are 5 possibilities. If we work this out, multiply, you actually get a lot of cancellation in terms of fraction arithmetic, but this will reduce to 0.5. So there's 5 different possible, it's going to be 0.5 would be the probability, so 50-50 chance that you would pick a license plate that ends in a even number.